Hello, everyone. This is IITT about geomechanics from micro to macro, a new episode, a new IITT interactive technical talk by ISSMGE. This is number 21, another exciting subject. I can't wait to see what we have to tell you, and hopefully you will like it. I like to introduce our speakers from around the world. I will start by sharing my screen. So here we have Professor Catherine O'Sullivan from Imperial College, London, UK. We have Dr. Angela Casarella, postdoc researcher from Gothenburg, Sweden. I just came from there. Dr. Estefan Garcia, University of Michigan, California, USA. Sorry, did I say California? Where are you at, Stefan?
In Ann Arbor, Michigan.
Ann Arbor, sorry, yep. Dr. Gareth Swarbrick from Sydney, Australia, geotechnical consultant from the industry. So we're bringing together from around the world people from academia and the industry to discuss this subject. I can't wait to see what's gonna happen. And as you know, dear speakers, feel free to interact and make this event and this talk special. I'm sure it will be. I will start with you, Catherine. The floor is yours. If you share your screen. And I will mute myself just in case there are noises behind me. Hopefully no bombs. So we have a ceasefire in Beirut now.
That's good, and thank you, Mark, for involving me in this. As you already said, I'm Catherine O'Sullivan. I'm the vice chair of TC105. So what I'm going to do in my talk is give a bit of an idea of what TC105 does, and then try and encapsulate the kind of research that's going on at the moment in micro to macro geomechanics. So we've got two objectives in TC105 in our official terms of reference on the ISSMGE website. And one is about sharing information about the behavior of soil particles, how they interact and how they interact with the environment around them, namely the pore fluid. And also clarifying the fundamental mechanics that underlie the complexity of soil response when we look at it at a macro scale, at a scale that I would say is it's kind of like the continuum scale. And then getting into a bit more deep, what we're trying to do is promote amongst the geotechnical engineering community, developing this particle scale fundamental understanding, looking at different complexities in soil mechanics behavior as are listed here, and link them to the fundamental particle scale interactions. Also promoting discussions about how we would use microscale measurements and DEM simulations to enhance what we do in terms of site investigation and geotechnical engineering practice. And also promoting best practice in terms of the use of DEM. And that's probably been one of the most successful recent activities of TC105. So led by the Japanese Geotechnical Society, there's recently been a round robin to assess whether people running different DEM codes or even different groups running the same DEM code get the same answer. So they've done a nice test led by Yukio Nakata on angle of repose simulations. And we had a really good discussion on that in our recent conference. And that recent conference gives me the opportunity just to show you who we are. So this is a photograph of, I think I need to activate my laser pointer. This is a photograph of everyone who was at Grenoble in September when we had our last TC105 conference. And two very important people in this photo are Itai Enav, who has just started as chair of TC105, and Cino Vigiani, who's really been a trooper in terms of being a core member of TC105 for many years. And he led what was an amazing conference supported by a fantastic team of people in Grenoble. And, you know, just to give the history, there have been a number of conferences since 2006. And now we're looking forward to going to China in 4 years' time. And I think what was really nice about the conference in September was the delta from Atlanta to Grenoble, because we'd had a longer period than usual. And I felt the change in what people are achieving in their research was remarkable. This really was an amazing meeting and really a very good opportunity for the community to showcase their work. So we have a website within the ISSMGE suite of websites, and you can find it. I always just get there by Googling TC105. But what's nice about our website is there are links to a number of videos that were recorded when Kenichi Soga was chair of TC105. And I think, you know, no matter where you are in the world, you can access these videos on DM in geotechnical engineering education. And what we're just starting now this autumn is to have our own LinkedIn page so that we can update people who are interested in our activities on an ongoing basis. Not everyone's looking at that webpage every day, but we're going to be a bit better at connecting with our community through this LinkedIn. So what I kind of like to be provocative to my colleagues at Imperial. This is a bird's eye view of our lab. And these are some images from a paper on continuum modeling by some of my colleagues. And just to say that what they're doing in these very sophisticated experiments or very sophisticated continuum models is they're describing how soil behaves. But I feel where I fit into the picture, and also everyone else in TC105, is we're really looking at why soil behaves as it does. And our toolkit is kind of particle scale observation, either by looking at images such as microcomputer tomography images, and Angela's going to, and Estefan are going to talk a lot more about this technique later on. Simulation, and this is an image of a coarse grain molecular dynamics simulation of the compression of clay. Also computational fluid dynamics to look at what's happening in the pores. And then bespoke experiments so that we can understand what's going on in interactions between particles. So this is work that was done at Imperial. It's nearly 20 years ago, looking at compression and shearing of soil grains. But these techniques have been developed, led to a large extent by Matthew Coop. And this is an image from Cashson Wan's PhD that was carried out in UCL over the past few years. So looking at how do we measure what happens at contact between grains. So this is kind of broadly speaking an overview of the types of techniques that you see if you go to a TC105 meeting. So over the past few years, I've been lucky enough to work with Fernando Patino Ramirez at Imperial College, and he's now starting in Georgia Tech as an assistant professor. And one of the ideas that Fernando had while he was at Imperial was to look at using techniques that we now have in widely available computer software like MATLAB to analyze geotechnical engineering journal articles to understand what really is the research that's going on in geotechnics. So he looked at 30 journals within the geotechnical engineering topic or theme. And then he did an analysis using an LDA topic model to identify or classify keywords in the abstracts, keywords, and title, and from these to identify topics that we could say were prevalent in geotechnical engineering research. So this is one of the word clouds he generated. And then Fernando, with me, we came up with identifying how would we describe this as a theme within geotechnical engineering research. And we said, well, these are all really about soil behavior. And there were 20 of these word clouds. And so we were able to identify 20 topics that are we can classify papers that have been published in geotechnical engineering into. And the most popular one of these was around soil behavior and soil properties. And that's really where my research and the bulk of the TC105 research has been placed. But what Fernando also did is he was able to look at the compound annual growth rate. And this is, how much are we seeing an increase in publications in certain areas? And it's not really a surprise to see that papers that we could call data science are kind of the most popular. And these papers on soil properties and behavior, while there are many of them, we're not really seeing a big growth in activity in that area in comparison with other topics. And where we are seeing a growth is in more applied research areas. If we take the data science out, we're looking at geohazards, offshore geotechnics. And I think that reflects some of the thinking in TC105 at the moment. What we really want to do now, we've developed the tools, we've made great progress, especially around fundamental behavior of sand, and we need to move up towards looking at these more applied areas. And the way we've structured our talks today, you'll see a transition from very applied, very small scale in Angela's talk, going into more applied areas in Estefan's, and then on to Gareth, who's going to talk about using these techniques in industry and very applied problems. So the overall theme of our TC is micro to macro, so we can look across the length scales, and we could start with thinking about electrons as a particle, but apparently, according to the New York Times, that's a relatively easy topic, and we should really just move directly to sand, where we see the more challenging problems. But we haven't really seen research in soil mechanics really at the electron level. But what we do see is quite a lot of work looking at the interaction of ions, atoms, and molecules. And the tools that we have there, if I can get rid of this stupid arrow, are DLVO theory, molecular dynamics, grand canonical Monte Carlo simulations, and potential of mean force. So, if you look at Jim Mitchell's work in the most recently published edition of Mitchell and Soga in his Fundamentals of Soil Behavior textbook, there's a very good explanation of DLVO theory. And this is an analytical approach to understanding. It gives you results about how the energy between two interacting clay particles varies with separation distance. And if we know that energy, we can work out an interaction force. And it's explained very nicely in this text. But what's happened, and these techniques have been around since the late 1950s, but in recent years, we're seeing geotechnical engineers exploit Monte Carlo simulations and molecular dynamics to really look at computational chemistry and its application in soil mechanics. And there's been a lot of work looking at water absorption and the interaction of water molecules with montmorillonite platelets, largely kind of driven by the fact that we're using montmorillonite in nuclear waste depositories. What's probably slightly of more interest to me personally is work such as this work done by Katerina Yanodo and her colleagues, where they're looking at immogolite clay particles, and then looking at how does the energy between these particles vary with their separation. And the reason that's of interest to me is it's this kind of information, and there's not that much of it, that allows us to go on and work up at the scale of individual clay platelets. So the challenges here is that DLVO theory, which is our big reference point in terms of understanding clay particle interactions, that has limited applicability. There aren't a lot of these simulations that give us energy as a function of separation distance for clay platelets. And these are the things that we really need in order to advance particle scale simulation of clay. And if we can get this going, that allows us to do platelet scale simulations. If we move up then to the clay platelet scale, our tools are scanning electron microscopy, atomic force microscopy, DEM, and coarse-grained molecular dynamics. So I think what's quite exciting about SEM has been around for donkey's years, but more and more recently, we see groups taking SEM and coupling it with quantitative image analysis to start to say things about fabric as clay samples deform, and the same with silt. And we've seen work done on clay platelets coming out of Madia Hattab's group in France. In UCL, Beatrice Baudet's been looking at the voids and the spaces between the platelets using these type of techniques. And I think that's very exciting. And what's even more exciting is we can use focused ion beam SEM, and that's a way of shaving off layers of clay, and that can give us a very accurate 3D image of clay. And Angela is going to kind of look at other techniques, micro CT, to give us this 3D pictures of what's happening in clay. So for the first time, we are now in a position where we can see what's going on in a clay sample in 3 dimensions. Atomic force microscopy, I think, is a very exciting tool. These are some images from the group in chemical engineering at Imperial that look at clay. So not in our TC105 community, but this is a tool I think we're going to see a lot of over the coming years. And the reason that's so exciting is it can give us an idea of the force separation relationship. And this is a AFM tip interacting with the edge of a kaolinite platelet, and this is a high salinity and low salinity, and looking at how that force changes. So that allows us to measure what's going on in terms of the forces between clay platelets. And then we have DEM. So these are some simulations from Glenn McDowell and John DeBono. So individual kaolinite platelets are modeled as assemblies of spheres. So this is really nice. We can get an accurate picture of the clay platelet geometry, but it's very expensive because we have to calculate the interaction between all the subspheres and the platelets. So another alternative that some of my students, Sarah Madeira and Yohei Nakamichi, have taken is to simulate the clay platelets as flat ellipsoids and use coarse grain molecular dynamics. And that allows you to start to look at the structures that emerge in clay and the sensitivity of the fabric to the chemical composition of the pore fluid. So all of these are images of kaolinite. So the challenges going forward are, DLVO theory has limited validity. We use it to interpret AFM data and also to develop our interaction models for DEM. We don't have a good handle on friction between clay platelets, but we know that's important at the same time. We need to look at very large systems so the fabric can emerge, and how we study active clay is not clear. And, there's opportunities to develop constitutive models and explain some of the really complex aspects of coupled phenomena. Moving up to sand, that's where the bulk of my career has been. We can use DEM or microcomputed tomography. So this is a DEM sample from work by Masahide Otsubo and Tom Shire, and they were trying to develop new experimental techniques to look at how much stress fine particles are transmitting in a gap-graded material. This is some ongoing work from my current PhD student, Jose Salomon, who's looking at how we transition from a fully undrained behavior in the black lines to a completely drained behavior. So with DEM, we can control volumetric strain in a sample in a very systematic way and have thought experiments that will be very difficult to carry out in the lab about how relaxing the constant volume constraint might affect behavior. And then this is a picture from a paper by Eddie Ando that I really like because it's showing how you can potentially use microcomputed tomography to understand some of the phenomena that underlie creep in sand and linking creep to soil particle cracking. So again, we need to know our system's big enough. There's issues around image segmentation, measuring our properties, and making sure that what we do is relevant to the broader community. And I think the key things that we want to do here is support the development of constitutive models, develop new experimental approaches, and extend the data sets we have. I firmly believe that these simulations should never replace experiments, but they can complement them to really advance understanding of soil behavior. Obviously, we want to look at upscaling, and one of the things, again, Fernando did when he was with me was use DEM and high-performance computing to look at horizontal penetration of a probe into soil. And the key issue when you've got something penetrating horizontally is you're going to have a drag force that resists the penetration and a lift force that tries to push it up. And Fernando had an idea that we could optimize the shape of the tip of a penetrating object to minimize both drag force and lift. So he ran his DEM simulations within an optimization algorithm, and he was able to come up, and this is the CPT as a reference point, with the topology that would give the minimum drag, the minimum lift, and then he came up with what he called a Pareto optimized solution, which is kind of the best of both worlds, and he found that looked very like a sandfish. And there's other examples, this is helical piles of large penetration problems that can be analyzed with DEM. And the things we want to look about is how do we get a big enough system? How do we use our boundaries intelligent enough so that we can get sensible results? But this is a real opportunity for looking at geotechnical problems, and there's many of them that have large deformation. And Gareth, I think, is really going to showcase some of the benefits of using DEM on large deformation problems. The last thing I'd like to highlight is the importance of coupling and the potential there is there. So these are some images from the lab in Sheffield and Liz Bowman's group, where she can do permeameter tests using a transparent soil, but also use small tracer particles so that she can track the flow of water inside in her model soil with transparent sand grains. And from a modeling perspective, we can do fully resolved computational fluid mechanics, that's expensive, or pore network modeling, which is very popular in petroleum engineering, but it also has a value in soil mechanics. And I think one of the areas that we really want to look at in the near future is using these tools to look at partially saturated soil and try to get a better handle on effective stress. But these simulations are not easy. There's a lot of issues with doing multi-phase CFD. These fully resolved computational tools, they're very expensive. And in the lab as well, whether we're looking at transparent soil or microfluidics, getting over issues around boundary conditions is difficult. And I think the opportunities here, as I already said, have been around effective stress. And one of the things we're really interested in Imperial at the moment is looking at non-Newtonian fluids and polymer fluids. So to wrap up, I just wanted to give an idea of where I think some of the opportunities might be in the next decade for this TC105 community. And I think we're really can see in our recent conference that we're at the beginning of some really exciting research on particle scale simulation and imaging of clay. GPU acceleration is something that now presents a real opportunity for us to look at bigger systems or to look at more complex systems. Open source software is going to enable a lot of research in this area. There's a big effort in Europe on the on-DEM cost network, which is really promoting good practice in using open source DEM codes. Obviously, we have AI and machine learning and image analysis, but also potentially in modeling and developing our contact models and developing our conductances in our pore network models. And I think the challenges that we have are getting a handle on what our interactions are in particle scale simulations of clay. What do we do with active clays? All the images I showed today were of kaolinite. There was one on montmorillonite, but other than looking at swelling of montmorillonite, we haven't done a lot in that space. Unsaturated soil, looking at multi-phase flow, and then going on to looking at coupled simulations with temperature. What happens when we have phase changes, when we have ice forming or melting? And that's, a big issue for many applications. Mixtures, we tend to look at either sand or clay. We don't mix them up. Obviously, we would want to do that to be more realistic. And then how do we develop our research to make sure that we have a societal impact or an impact on industry? And, we want to be thinking about things like the SDGs and really, we're civil engineers. These are the things that we should be targeting, having an impact on these. So to wrap up, I would just like to thank the TC105 community. It's been great to be a member of this, and I've tried to showcase research from different groups around the world. These are the people whose work contributed to, who worked with me, whose pictures from their research I've shown today, and these are people who funded my research. But just to wrap up, I'd like to say that for the rest of this session, we're going to have a real micro to macro transition with Angela looking at clay, Estefan then looking at fabric and sand, and moving up to Gareth looking at field scale applications. So thanks for this opportunity to highlight our activities. I'm going to stop sharing and leave you, Marc, to pass me on or pass on.
This is fantastic presentation. Logical from the time to the size. I mean, you're putting everything together beautifully. Thank you so much. Also, thank you for being active with TC105. Those videos you mentioned at the beginning should be part of the virtual university, where we have hundreds of webinars, lectures, open access. I don't know if they are there already or if we can fit them. Marcelo, if you can talk to Marcelo, the chair of TOC, see how to fit them.
Okay,
It
I'll
would be
liaise
great.
with Marcelo on that.
Share,
With Kenichi.
not move them, just have links to share them.
Okay.
Thank you so much. I think you already introduced the rest of the speakers with Angela. Are you ready?
Yes, I'm ready. I can share
It's
my.
yours. I'm learning so much tonight.
Can you see my screen? Yes, perfect. Yes, so I'm gonna jump right in from where Catherine just finished. Thank you for introducing me, Catherine, and thank you for this opportunity of sharing our work from micro to macro. I'm gonna explore a very, very small scale in my presentation, and specifically I'm gonna talk about clay micromechanics, giving a little bit of an experimental insight and showing you what's the work that we have been doing at Chalmers with respect to investigating particle-to-particle interactions of clays. So our capacity to simulate the soil behavior is often quite good at the continuum scale. We usually use balance equation, constitutive relations, and we couple them with initial and boundary conditions. And let's say that we have a big issue respect to the constitutive relations, which is the fact that we are sometimes, it's very difficult sometimes to characterize correctly the soil since natural materials observe no quality assurance criteria. This means that in order to overcome the soil characterization, what we have been doing in the past decades, at least for discrete, for granular materials, has been to use a discrete approach. So we have been evaluating the experimental investigation of the kinematics of clay sand particles, for example, with micro X-ray computed tomography, coupled with the numerical techniques such as discrete element method. And then we can also use a combination of the two, which is has emerged in the last decade, which is level set DEM, in which we are trying to build up a digital twin of the sample that we test, we scan in the microtomograph and try to simulate the behavior of sand in order to have a virtual laboratory, let's say, of our and conduct our experiments virtually. But my question now, and this the question that I'm gonna try to address along this presentation, is can we do the same with clay? Can we observe the micromechanisms and then simulate them at the particle scale to inform constitutive modeling? Let's have a look at this. If we scan a clay sample, a very small clay sample, the same size of the samples of sand that we usually scan in an X-ray microtomograph in a lab, for example, the one that we can see in the picture here is the one located in Grenoble at Trois Essers. What we can do is go down to a pixel size of 25 microns. But 25 microns, if allows us, is this gonna start? Doesn't look like. Nope. Yes, well, it was a triaxial compression of this clay. But you can already see that if we scan this material, if we scan a sample of the same size of sand, what we can observe is the kinematics of clay particles, and so the shearing. We can identify the shear band clearly of what is going on at the micro level. Instead, what we can see when we scan a sample of clay at this pixel size is still a continuum scale. We cannot identify individual clay platelets. So what we can do with respect to that? We have to go smaller, and to go smaller, we also need more energy. Meaning that first we have to reduce the size of our samples, but second, we also need a larger amount of energy, and that's why we need a synchrotron source. So what we did do is going at ID16B, which is the nano beamline available at the European Synchrotron in Grenoble, France. And we tried to scan a granular monomineral model clay called specified kaolin clay in order to try to see if we could resolve individual clay platelets. And what we could actually see is that going down to a pixel size of 25 nanometers, so we are going 1,000 times smaller, what we can image in 3D, this is only a slice of a 3D scan that you can, of which you can see the network here, we can actually image clay particles and aggregates. And at this point, what we would like to do is trying to mimic the same process that we actually do for coarse grain materials. And the biggest interest that we have at this time, since we haven't been able to look at it in clays, is clay fabric and how this would affect clay behavior. So what we did was starting from dry powder or specified kaolin clay and saturating the clay with two different environments, an alkaline water environment and acidic water environment, in order to induce two different types of fabric of clay. We perform 1D consolidation of these two samples, and then we perform undrained unloading. And what we did do, leaving the sample in saturated condition, was to core out a sample of a diameter 300 micron and image it. And what we did see, for example, for the alkaline environment, was that the 3D image here, I only report one slice of it, shows clearly that the particle present the fabric in alkaline environment shows particles very much aligned in the horizontal direction, which is the horizontal perpendicular to the 1D consolidation that we performed at the beginning. And this is very much what we expected, since it is consistent with the DLVO theory that Catherine was mentioning before during her talk. What we know according to the DLVO theory is that in alkaline conditions, we have the distribution of surface charge of the particle enhances the net repulsion between particles. And so when this repulsion is enhanced, the minimum energy situation texture in which clay particles tend to arrange is the face-to-face packed fabric. And this is exactly what we can by eye notice in this graph. But we can not only notice it by eye, what we can do is quantify it. What we would be doing for coarse grain materials would be to, for example, at this point of the analysis, to segment those particles and try to analyze contact network, shape, orientation, and so on. However, as you might be noticing, this scan is particularly complicated. The amount of particles is huge, and the shape is very different. So we would need AI to perform a segmentation and labeling of these scans in 3D. What we can instead do would be to just focus on one of the possible information that we can deduce from those scans, which is particle orientation. And what we can specifically do is looking at the variation of gray levels in the 3D image in order to understand the orientation of particles. And in order to determine two angles, which are the polar angle and the azimuth angle, which would describe, in our case, each voxel with respect to a Gaussian interrogation window around it. So what we can do is for each voxel determine two angles and track down a map of the orientation of each voxel in the image. And what we can see in alkaline environment is exactly the fact that the color map shows how all the particles are very much oriented along more or less the same direction, the same combination of theta and phi. And so therefore, we can even quantify how much, which is the preferential orientation of our fabric. Therefore, consistently with the theories of colloidal science that we are used to, even if clusters of particles, so assemblages of particles oriented in the same direction exist in an alkaline environment, they align all in a similar direction, in a subparallel direction. We can compare the fabric that we analyzed in pH 9 with the fabric of clay in acidic conditions. And what we can see already by eye is that there is a way more randomized and random orientation of the particles. The sample looks way more looks way less anisotropic than the one in alkaline conditions. Indeed, this is exactly also what we expected, since according to colloidal science, the acidic environment induces a non-uniform distribution of particle charge, and the arising of possible positive and negative poles, positive and negative surface charge along the clay particle itself. This interaction, electrochemical interaction between positive and negative phases and edges, would create a way more open fabric, which may promote some edge-to-face interaction of particles. Therefore, if we try to use the same tool that we used before in order to analyze the orientation of particles in acidic environments, so with a pH lower than 6, what we can see is clearly that some blobs in the orientation map arise, and they kind of show the presence of some areas in which particles align subparallel to each other, and then those clusters that are formed by aligned particles arrange in an edge-to-face manner, creating some macroporosity. If we look at the comparison between the two, then we can see that in alkaline conditions, this kind of aligned behavior is also confirmed by some of the numerical research in coarse-grained molecular dynamics carried out at Imperial College London by Nakamichi et al. And so this could allow us to make the link that I was mentioning before between the clay micromechanics and the particle scale clay mechanism that we have already been seeing in coarse-grained molecular dynamics in granular materials, and can be eventually reproduced for fine-grained soils in this case. Indeed, I will conclude saying that there is a possibility, at least for the this monomineral monogranular clay that we have been studying in this context, to move towards level set coarse-grained molecular dynamics and try to simulate, to mimic the same process that we do for coarse-grained materials. What's missing though? Since clay is very much different from sand, some other techniques, complementary techniques, are required to study and to inform this level set coarse-grained molecular dynamics. For example, the atomistic form microscopy that Catherine mentioned before, but also it's very much important at this stage, not only to be looking at fabric of clay, but also at the 4D microstructure monitoring, 4D meaning 3D plus time monitoring of clay particles, evolution of clay particle fabric with the in situ nano X-ray tomography, but also with wide angle and small angle X-ray scattering. And then I will conclude by thanking all the people that contributed to this work, of which picture I show here.
Angela. Wow, amazing. Where we're at now. So I come from a contracting background where we measure precision with centimeters, knowing that the drill rig of the pile has a tooth that's the size of my hand, even more. And then when I go to the classroom, I beg my students, imagine yourself, you're an ant. Now I have to tell them, imagine you're a bacteria.
Indeed, indeed.
And so,
The ant is
especially
way too big.
no, amazing with the azimuth and the orientation. My question is, why did you decide to test with two different acidity to push the particles on purpose in different directions, or?
Yeah, so we decided to investigate the fabric that would result from different pH saturation condition, since we knew already at the microscopic level, not at the microscopic level, or at least we have some investigation at the microscopic level, specific also for this clay, space white kaolin clay. However, all the investigation that have been performed were in a non-saturated condition. So in this case, we wanted to observe clay fabric in saturated condition for the first time. And since we knew already what we were expecting, let's say, we tried to investigate differences in pH and observing so the difference in fabric, in order to then try to eventually gather information on also the simulations that have been performed on the matter.
So you start with dry powder and then you saturate slowly with two types of fluid?
Yeah.
Like water with different acidity?
Yes.
I see. Very nice.
Thanks.
Oh my gosh, I am learning so much this time. Thank
I have a
you. I
question.
think Stefan is next. Gareth, you want to say something?
Yeah, just a question to Angela. Fantastic presentation. Thank you very much. Are you looking to increase the energy from the synchrotron? Is that where you're heading?
No, unfortunately not. I think I mentioned, I mentioned it here. So unfortunately, clays, especially the clays that we have been looking into, are soft materials, meaning that the too long exposure and then also an increased level, an increased amount of energy would damage the sample. And indeed, we have been starting looking in some in situ nano XCT, as I show here in the picture. This is a nano compression cell. It performs 1D compression of clay in drain conditions. However, we have been having some difficulties in imaging those kind of tests. So we are trying to monitor the evolution over 1D compression, but the too long exposure of the sample creates some serious damage. And therefore, we, of course, end up with having blurred scans. And so we are not able then to eventually perform image analysis on it. But we are trying
Yeah, that's exactly where my next part of the question was. I was thinking you're at a scale where Heisenberg says you start to affect your sample, right, with the investigation technique. And I thought you were probably approaching it, but you've exactly discussed that issue. Interesting. Thank you.
Thank you for the question. I will
Stefan,
then.
are you ready?
Yes, I am ready. Let me, we're almost ready.
What is yours?
I'll pull it up soon. I could, I think I could quickly in one sentence summarize my talk as what Angela said, but now to a slightly larger size. Let's see. See, can you, oops. Oh, let me fix that again. There we go.
You were sharing, okay.
Okay, excellent.
Yeah, yes.
So so yeah, in this talk, you can see some of the same techniques of X-ray tomography, also at the University of Grenoble, some of the same collaborators and the same software of the SPAM, the software for practical analysis of materials. So it's I'm really fascinated to see these techniques applied to such a fine scale of materials. So my talk is going to focus on coarser grain materials, the things that you can generally see with the naked eye, anything ranging from sands, gravels, cobbles, and in some cases, even boulders. And now, when I'm referring to fabric, I'm more referring to generally to how grains of different shapes and sizes are packed together. And the first list here on this slide gives some specific components of fabric. But in nature, the fabric of a natural soil deposit is a product of how the soil got there, including all the processes that brought the soil to where it is and all the factors that altered it over time. And to emphasize the significance of fabric, especially for focusing on these coarser grain materials, I'd like to share this image courtesy of one of my mentors, Professor Nick Sitar, where this image shows two piles of the exact same source material. Yet these cobbles here, and these cobbles here in the pile on the right has a systematic orientation of its grains that stands at a much higher angle of repose than the pile on the left, which is just kind of randomly dumped there. What this signifies is that the difference in strength of these two piles of the exact same material is a direct function of its fabric, or how the grains are packed together. Now, we can see and utilize the effects of fabric in engineering practice and in geological and geotechnical investigations. Most geotechnical engineers are familiar with one fabric component, which is the relative density of a soil, or the relative amount of void space in between solid grains. And in this talk, I'll show some results of modeling surface fault rupture. So I like to show these images from the work of another mentor of mine, Professor John Bray, where these schematics of strikes of fault rupture in map view and cross-sectional view show generally how stiff soils, including those with high relative density, tend to localize shear deformation into clearly delineated fault traces and shear zones, whereas more ductile soils, including those with relatively low density, tend not to localize deformation, but instead produce broadly distributed warping of soil without much distinctive shear offset. And we can often see through stress strain curves generated from laboratory tests that denser soils tend to be stronger and stiffer than looser soils, but relative density is not the only thing that determines a soil's strength during shearing. For example, a circular failure surface through soil, whether in a slope failure or a bearing capacity failure, shear perpendicular to soil bedding planes along the more vertically oriented sections of the failure surface, where we tend to see more triaxial modes of shearing. The soil tends to be stronger when shear propagates perpendicular to that bedding, and hence perpendicular to the orientations of the long axes of the grains. Whereas, say, at the bottom of this failure surface, where we have a more of a simple shear mode of deformation, shear tends to propagate along the bedding layer, or in other words, parallel to the elongated axes of these grains, and hence the soil tends to be a little bit weaker in that case. And this is still shear going through in many cases, the exact same material with often the same relative density, yet they have distinctly different shear strengths based on how shear propagates relative to its bedding orientation. Now, to investigate the mechanics of how fabric influences soil strength and deformation behavior, as you just saw, many researchers rely on tomographic techniques. In my case, I'm using the X-ray tomography facility at the University of Grenoble with some familiar names that you've seen in the previous two talks, including Professor Nick Sitar, Professor Cino Vigiani, and Dr. Edward Endo. And in this project, we specifically focused on the intact fabric of relatively undisturbed sand samples from Treasure Island in the San Francisco Bay of California. Just for some background context, during the Loma Prieta earthquake back in 1989, liquefaction was observed in anthropogenic hydraulic fill, but not in a natural sandbar or shoal deposit. And we hypothesized that the difference in liquefaction resistance was a result of the material's fabric. So this stress strain curve shown here is accompanied by X-ray tomography images performed at the University of Grenoble. And we can kind of see how that shear localization really doesn't begin until reaching the peak strength seen in the stress strain curve. And in this work, we used the software SPAM developed at the University of Grenoble to identify and label individual particles so we can track their translation and rotation and overall kinematics over time, allowing us to see, for example, on the right, how the grains rotate and reorient during shearing. Now, if we can track those grain orientations during shearing, we can also quantify the fabric within the shear zone at different stages of deformation. We can take those quantified grain orientations at different stages of triaxial shearing and visualize the fabric through these stereo nets shown here. So in this case, I'm looking at how the long axis of each grain is oriented relative to the shear band. And each grain will have a complex shape with a long, short, and intermediate axis all orthogonal to each other, as indicated, where the long axis is indicated in the bottom left figure from OTA 1972. And if I associate a unit vector oriented along that axis, I can plot that unit vector on a lower hemisphere as shown in the upper left figure here. And then I can take a two-dimensional projection of that lower hemisphere called a stereo net and plot the intersection of that unit vector with the hemispherical boundary, and it plots as a point on this stereo net. And the contours on the right over here represent the density of unit vector orientations for those grain long axes. And the orientation of the shear band itself is represented by an arc, as indicated, for example, here within each stereo net. And for two separate intact samples of Treasure Island Shoal that I'm just labeling as sample 1 and sample 2, the first column here represents the initial fabric in terms of grain long axis orientation. And the second column here represents the grain orientations within the shear band at a fully softened state, effectively representative of the critical state. And we can see that at critical state, the grain orientations cluster at a similar location, approximately dipping slightly above the shear plane. And these the location of where the grain orientations are clustered at the critical state are distinctly different distinctly different from where the grains were initially clustered, which suggests that the grains with any initial fabric will reorient towards a common and unique critical state fabric. Now, the challenge with studying fabric changes, especially with respect to a fabric produced by natural depositional processes, is that creating a specific fabric representative of a natural soil deposit is quite difficult to do in a laboratory. For example, many laboratory samples are pluviated such that the long axes of each grain kind of have a random orientation across all horizontal directions, which is not quite representative of what we might see from a natural soil deposit where the grains tend to have a preferred orientation that is not random. So to really look at how fabric changes with any given initial state, it's much easier to at least look at virtual analogs. And here's where I'm bringing the discrete element method with these simple shear simulations shown here. And we can see that through the stereo net here representing the long axes of the grains in this virtual analog simulation, that those orientations are systematically reorienting from some initial state towards the direction of shearing. Now, I'm going to transition up to a larger scale and sort of allude to what Gareth will present shortly. But these simple shear simulations can these simple shear simulations can provide the stress, strain, volume change behavior relative to shearing induced by nature, such as during earthquake surface fault rupture. And in this work, we're focusing mostly on the component of fabric associated with the relative density. And the discrete element method seamlessly captures the salient features of shear deformation in loose and dense granular materials. We can see that shear deformation in this dense material is quite localized, whereas in this loose material, it's quite widespread. And by using some simple non-spherical shapes that at a minimum capture inhibition of rolling about all three Cartesian directions, we can further capture mechanisms of grain interlocking that contribute to soil deformation behavior. And we take this method at one scale here and upscale it to the scale of several meters, which we do in this model by applying an acceleration due to gravity of 100 Gs, as one does in a centrifuge experiment, to represent the stress associated with several meters of soil, in this case representative of a depth of 20 meters. Now, folks in structural geology and tectonics have actually been using the discrete element method to represent analog sandbox models in virtual space for the last 30 years. Now, with the aid of high-performance computing, we are only recently able to do this with tens of millions of discrete elements in 3D space. And I'll briefly show some of the results of this work. And I'll note that the key features I want to point out are those that can be explained from observations at the smaller scale. For example, loose soils that tend to have a contractive shear response, loose soils that tend to have a contractive shear response in, say, element scale simulations, such as in simple shear, they tend to produce features such as ground surface subsidence. Yet also from reconnaissance investigations, such as what I showed from the previous Bray et al. Work back in '94, we still tend to see these N-echelon shears located along the surface trace of the fault, which tends to produce these regions of ground surface upheaval. Whereas in dense soils, we see sort of a more complex shear mechanism where shear tends to initially propagate over a very broad region, but shear becomes inadmissible over these wider zones and tends to translate or transition to a region more closely associated with what we saw for the loose soil. And that's consistent with what we expect from critical state soil mechanics, because dense materials tend to dilate and loosen the soil, producing a much weaker zone that is easier to propagate through. Now, I'll finish this talk with just some challenges where there is a challenge with simulating tens of millions of particles, which is why this work has to rely on high performance computing. And we can clearly see that with up to 85 million elements as opposed to 1 million elements, we tend to see more fine features of shear deformation. But what I suggest is that rather than treating every element as a distinctive particle or grain, we can treat elements as representative of masses of soil. And that way we can still capture some of the key features associated with critical state soil mechanics, such as contractive versus dilative behavior in relatively loose versus dense soils. So I'll finish up with some acknowledgements. Here are the students that have worked with me on this research. I do want to acknowledge some of the many friends, mentors, and collaborators through these geotechnical engineering and soil mechanics communities that have helped and guided me through much of this work. And now I will pass it on to the next speaker.
Estefan, fantastic. Macro is a little bit something I can understand better than the micro. You reminded me of the rock mechanics course I took, orientations, but this is amazing with the videos, fantastic.
Estefan, I had a question around, is all your simulations at the moment, are they dry? Do you include any pore pressure?
Yes, everything is dry right now. We don't yet have a mechanism for including excess pore pressure. I think there's many mechanisms of including hydrostatic pressure in general. But yeah, modeling something like liquefaction directly or modeling the water pressure directly is quite a challenge. What we've seen, what people often do is control volumetric conditions to maintain constant volume conditions during shearing to kind of mimic the effects of excess pore pressure.
I was already very impressed. I'd be even more impressed if you managed to include pore pressure. It would be quite a challenge, I can see.
Gareth, are you ready?
Yes, I'm ready.
Stefan, can you stop sharing? Yeah, okay.
Let me know when that comes up.
It's ready. Floor is yours.
Great, thank you very much. So I have a slightly difficult challenge in going from some fantastic, amazing research shown by Catherine, Angela, and Estefan into what we're currently using. And at least from my perspective, I've actually was an academic for half of my career, and now the second half has been as a consultant. And one of my challenges is to look at what we can bring to the table in terms of analyses and other tools that help us sort of shape and confirm our engineering judgment a lot of the time. So I'll go through some of the things that I've been exposed to and that I've seen others do. And look, there's a lot of similarities with what we've already covered, which has been fantastic. This slide for me sort of summarizes my experience anyway with the sort of technologies and research that we've managed to apply thus far. Some of the key things that we work a lot with are things like backfilling of material. So looking at the actual behavior of granular material and how it performs in realistic situations, because the continuum model that Angela spoke about is not always very exact or doesn't really describe some of this sort of material. One of the common applications we look at granular flows is things like backfilling. So old mine voids is a very common situation where we're trying to get material into a void to make the void safe, to prevent too much deformation should that void collapse over time or due to external loading. So how do you get that material to flow into that void and actually fill that void as best as possible is one common way of doing that. And I'm going to show you a little problem we had recently with a tunneling in Sydney where we had a very old sandstone lined blockwork drain, which was heritage protected. All of these sandstone blocks were not connected to each other by any, they weren't structurally connected. They were simply loose blocks arranged in an arch. And we did quite a bit of modeling on this, but what I'm showing you here is a 120 scale model, because we actually had to end up doing a scale model to try and convince ourselves that the modeling that we're doing, which was based on continua, had some sort of defensible component to it and was reflecting what we actually might see in reality. Interestingly, this became an internal competition inside the company. So we all had to guess and see how well or how bad our predictions would be. And one of the best simulations that came up with was actually using particle flow code to actually show what that behavior might be and how that arch might perform if that material was removed, and how that support would become that support would become no longer isotropically controlling that archway. Another common way that we use discrete modeling and discrete research is looking at things like rock falls. So we often build sometimes very high slopes up to hundreds of meters high, and we're concerned about blocks that may become dislodged from those slopes. And what's the travel distance of those blocks? And so understanding the size and the travel distance allows us to design fences and other types of systems that can retain those blocks and prevent or certainly limit the size and the impacts that they might cause should they become dislodged. So by using approaches and modeling, we can then look at different types of retaining systems and decide which ones might be the most effective and most appropriate for that particular geological environment. I was very excited to hear Catherine talk about unsaturated soils. As my background research is in unsaturated soils, and I think that's a fantastic emerging area that I can really see discrete geomechanics becoming a force in, because we have this very complicated particle fluid interaction. You've got multi-phases within those particles, and you have an issue with unsaturated soils where the fluid becomes discontinuous. Either the air component becomes entrapped, so you have entrapped air, or you may have a discontinuous liquid component, typically water. And there are no decent models that actually capture that effectively at the moment. And so it becomes an issue whether you have the extremes of very low air concentrations, high fluid concentrations, and the opposite where you have high air concentrations, low fluid concentrations. The models break down because it's no longer a continuum, and you're no longer able to model that behavior with the sort of models that we currently have. I'm going to talk a bit more about this application because this is quite well developed in terms of discrete mechanics and discrete modeling in geomechanics, and that's rock mass behavior. So there are a number of reasons why the DEM approach has been adopted quite some time ago in rock mechanics and being continuously developed since. And I'll go through some of those reasoning as I take you through some of my next slides. So looking at the rock mechanics scale, we're sort of sitting here. We start in the sort of gravels, boulders region, but in fact, our rock scale, as we, if you like, zoom into that or zoom out of that scale, we can get to quite large scale features that can dominate that rock mass behavior. And we even start talking about tectonic features and things like that. And Estefan spoke very well around faults and the interactions of particles and other geological features as a consequence of that fault movement. So I'm going to sort of delve into this area and how that's being looked at and how these tools are helping consultants in those regions and designers. When you look at geological features, there are a lot of different types, and I'm not a geologist by background, so I'm not very qualified to speak to many of these, but just to give you a sense of, they're quite complicated. They have a lot of different types of shapes and they interact in different forms, and the geologists understand best on how they were formed and how they might behave under additional stress and additional strain. And there's a lot of quantification going on about those different types of structures, how they in particular intersect, or more importantly, don't intersect. Sometimes they're truncated against each other. Sometimes they become offsetting, and sometimes they actually form crossing. So understanding how these were formed is what the geologists spend a lot of their time understanding and being able to then communicate into some of the modeling that is then used to try and reflect and try and anticipate how these structures might behave. How do we collect this data? There's a few different ways. So most commonly now we use something along the lines of the scanning electron microscope, but at a macro scale. We use photogrammetric techniques. We use LiDAR that allows us in 3D to pick up different defects within a particular mass of rock. And we can then create 3D images and 3D constructs in real space. So this is in the actual scale of the actual features themselves. Another way we do it is we do downhole tomography using acoustic televiewer, optic televiewer techniques. And those techniques allow us to pick up the structure that's within a rock sample and then interpret that particular structure, its orientation, the defect, and the inclination of that defect as well as the type of defect. That's also very important. So we end up, and this is a real case on the dam we've worked on a few years ago, where we can create from boreholes actually representations of different defects, and the different colors represent necessarily their type or what rock unit they lie in. And so we have quite a nice distribution in 3 dimensions. We are trying to understand, in this case, how those features might connect and how they might interact with the dam structure once it's loaded by water, by earthquake, by other means. So we have a bit of an issue though, because even with a very high frequency of data collection, with downhole sampling, with surface mapping, we may be using hydraulic methods or other methods to anticipate these structures, we still have a lot of gaps. So this is quite a dense model of a discrete actual measured fracture network within a system. This is looking at tunnels. We've got small joints, we've got shears, we've got larger scale faults running through our particular model environment. But we're missing a lot of areas in this design. Only the areas we can get to, only the boreholes that we can put down with time, money, with access and things like along those lines. So what we then move to is to create a statistical representation of that information. So by taking all that data that we've collected and understanding what the distribution of orientations is, what the distribution of inclination, where it's located, relating that to each rock mass type, each fracture type, we then create what we call DFN or discrete fracture network models. And these realizations, if you were to put a borehole anywhere within this model, you would end up with the same distribution of inclination, of orientation, of defect spacing, of defect type. But they are not exact, of course. They are just a single realization of what actually fits the data. Because we have this big sort of lack of data and we have this missing information that we have to then interpret. But this is the way we best solve this particular issue, particularly at this larger scale, when, as I say, we can't scan the entire subsurface. We have we have a limited amount of resources and techniques at this time to be able to do that. Once we have these realizations, we can then do a lot of other things. We can then pretend that they represent a realistic situation, a deterministic situation that we can then run through different analyses. A very common one here is when we're looking at tunnel design. So with tunnel design, we can create that discrete fracture network. We can then visualize a tunnel through that network and deterministically find out all the wedges that may be formed, in this case, in the roof of the tunnel and the sides of the tunnel, which intersect with those defects. So we work through this sort of workflow that's shown here. We look at finding those wedges. We can then analyze every single one and see if they were likely to fall from the roof into the tunnel excavation itself, and what the factor of safety associated with those is. And that includes things such as the strength of the rock, the water pressures, and all those sort of things. But there are a realistic realization of what may happen were we to tunnel through that rock mass.
Gareth?
Yes?
Sorry to interrupt. Can you go
Sure.
back one slide? Yes, these maps in 3D, were they obtained by like geophysical methods or?
We do use just geophysics sometimes, but mainly we use this data. So the borehole interpretation is
So
one
from
of the
the
most common
borehole,
ways. But then this is what we do is we take all these structures, by statistical analysis, we
then
work out,
expand it.
yes, we generate a realization which is a fictional, but as I say, it's designed so that when we subsample from this, we end up with the same distribution of the defect type that we measured in boreholes, surface mapping, geophysics, whatever we can get our hands on to work out where these defects are. So this
So
is
you bring techniques to complement each other, and then
that's right.
you build
And this software that's shown here, FracMan, its job is to statistically generate a DFN which mimics the data that we've found. Yeah,
so
thanks for that, Mark.
FracMan is a software that you input all the
Yes,
data in, and it
input all the
generates
data,
the fill in the
but
gap kind of.
fill in the gap, but statistically defensible. So it will work out spacings and orientations and all those other features that exactly match your data or very closely match your data. But they are one
So the more
realization.
data you give FracMan, the better.
That's right. It even looks at what the total area of fractures is, what the total volume of fracture is. So it looks at lots of different metrics in that analysis, and so that it then can create for you these DFNs that, as I say, match your limited amount of data. We're working on a large scale. We have a limited amount of investigation techniques. So
and
I
is
sort of
FracMan developed at PSM or?
No, it was developed by Golder. Golder developed this
Okay.
software probably about sort of 10 years ago, originally developed for the petroleum industry. So they developed it to work out fracturing and how to actually do oil recovery.
To estimate, yes. Very
Thanks for the
nice.
question, because I might have skipped that a bit too quickly. So thank you for that clarification. So once you have this DFN, you can obviously see the sort of things we can do. This is actually all the fractures generated along the tunnel alignment, which we then intersected in step 2 to create the wedges. Then we can actually look at all of those wedges, because this is not it's not exactly what we see. It's a potential solution to what we see. So what we then do is look at all the different wedges and align them statistically to look at their mass and work out what the distribution it might be under that scenario, and then work out what the largest block is that we say make sure that 99% of all blocks are going to be smaller than this block, for example. And then we design our tunnel lining so that we support that particular block size. And then we go through that entire process again with a different realization using FracMan. So we say, FracMan, generate another model that fits all my data. And we do the whole process again. And we repeat that over and over until we end up with the same statistical distribution that matches, that's saying, yes, we are converging to a solution, which says that we're pretty confident then we have actually a realistic distribution, which we can then go and design our tunnel support to. Does that make sense? Great. There's some challenges to that, and I think this is where the particle scale is really going to help us. So one of the common challenges is that the DFNs that we create, they are so deterministic that if they don't line up properly, say in this particular case here, I'm sorry, my slides are a bit bleeding over each other at the moment. If they don't overlap properly, then we don't form proper structures, and therefore they're not analyzed as such, because they don't become a deterministic block. So at the moment, there's a lot of research going on how do we overcome the fact that this fictitious fracture network, which does match our data, but may end up with very small gaps in some of the defects, therefore does not form deterministic structures, therefore does not form mechanisms. And is that correct? So maybe if they were a little bit longer, they would form mechanisms. So trying to look at how these rock bridges can be overcome in analyses is one of the common things we're looking at the moment. We're also looking at the other ways that ground is fractured. So not only through this situation where you may have movement, stress and strain may then connect up these rock bridges, as we call them, but also there's other types of techniques which are being used to purposely fracture ground, such as hydraulic fracturing. Hydraulic fracturing is used in the petroleum industry. It's used for things like gas recovery, oil recovery, and even injecting remediation things such as iron filings, which can reduce the amount of contaminants that get propagated through fractured rock. So the challenges we have at the moment is taking what we think is a well-developed field, this discrete fracture networks, and how does stress and strain and pore pressure change those networks? So as I mentioned, it's analogous to particle crushing or fracturing of your particles, which I know is a very prominent and a very highly required area of research that others have spoken about that's ongoing. So we're looking at how do we form new fractures and new surfaces and new flow pathways. And we know that the flow through fractures dominates in the rock mass, so this is very important. So we start with continuum type models such as FLAC, which is run by Itasca. We have discrete models which look at discrete blocks. So our DFN can create these blocks for us and we can analyze them. But what we want is something that goes the next step, which can actually allow you to have discrete or planes of weakness, but also have the rock mass which can fracture, which can actually break up and create new blocks and new mechanisms. And we have one at the moment called PFC, and I think a lot of people would know what PFC is, particularly the researchers today, but many others. And PFC is designed to actually make that bridge between the ability of going continua, which is what these single blocks are, but to create those new fractures as a consequence of strain and stress and even flow pressure. Some of the approaches that are around. So this is a PFC style approach. One of the issues we have with PFC is that when we're working with a large scale, our particles have to be large scale because of computational limitations. So we have to make fictitious properties up for those elements within PSE to try and reflect how they might represent larger scale properties, because we can't really computationally model those smaller grains. But we're at least able to calibrate these models to what we see in terms of rock testing or other types of testing and get a fairly good representation. These are other types of models that are out there. This is a hybrid model, which is actually a finite element model, which can actually create new fractures. As in this case, there's a stress fracture which is going through that model. This is developed, this is called the discrete lattice spring method by a researcher who was at UNSW some time ago, now at Monash. And Geo can actually represent this fracture generation by this type of technique, which is very interesting. Other types of spring models exist. This one here is a sort of more simplified version of that, if you like, where all the linkages are springs and the springs break and they cause new fractures to be generated. And this is another type of method called the scaled boundary finite element method, where again, we're looking at sort of discrete, if you like, or continuum elements that can become discrete elements through stress and strain propagation. The state of the art is sort of normally considered this what's called a synthetic rock mass. And this is really where you combine this bonded particle model and your discrete fracture network together and create what is commonly termed the synthetic rock mass. And this synthetic rock mass is being used to try and solve exactly the sort of problem I showed you on my first slide, where we have discrete fractures and they can lead to mechanisms being formed, but there's also, of course, fracturing and disassociation of that material as it goes through that strain process as due to that failure mechanism. So this fracture growth, it can handle fracture growth, it can handle strain and fluid pressure, and it generally can mimic quite well what we see on site. We still have an issue with calibrating these models. They're not actually modeling the grains in the rock, they're modeling larger size particles. As I said, for computational reasons, we are limited to that. So I just want to finish with my first slide and just summarizing where we're at, as I mentioned, the sort of flow of materials is something we use quite routinely. Travel of rock and failure of rock and understanding rockfall and travel distance is another one. Icy and saturated soils is a really important area where the research is going to help us go further in that area in understanding and modeling in the future. And as I mentioned, rock mass behavior is an area that's fairly well developed and fairly mature. Thank you very much. And thanks very much, Marc, for this opportunity. It's been fantastic to be able to speak in this sort of forum with the company that I'm surrounded by. Thank you.
Gareth, I should be the one thanking you all. You put all this research into practice and showed us what's being done, at least at the macro level. Guys, I learned a lot this time. Thank you so much. This was an amazing talk. I don't know if you want to add anything before I stop recording. We're all okay. We went a little bit overboard, above 1 hour, but this is normal with such a nice topic. We should have probably made 2 episodes, but it's okay. I want to thank you again for volunteering and preparing all your slides, and it was really informative, and thank you so much. We should have this episode launched in our social media and published probably in the coming 2 weeks. But you will know I connected with all of you on LinkedIn. Some of you already saw the invite. So let's stay connected. ISSMGE is your international geotechnical family, and you're always welcome there. Thank you so much.
Marc. This was
Thanks.
Thank you. Good to meet you all.